So I'm going to share great experience that I've been having at NCAR, working with Doug and Claudia, and thinking about the covariance structure of climate model outputs. So the main goal of this work is to find new realizations of future climate. And for example, over here, the image shows the spatial field of one of the climate variables from the NCAR Earth system model. And anybody who has worked on the Earth system model knows that it takes several months on a supercomputer to get climate model outputs. Additionally, there are different groups around the world that develop these climate model outputs, and they all give a different outcome of the future climate. So for example, this image shows the spatial field for Max Planck Institute in Germany. This shows for the Meteorological Institute from Japan, and then the NCAR. And they all show a different output of the future climate for the same climate variable. But because we have this ensemble of climate model outputs, we can think about how to find this distribution, which will give us a new realization rather quickly. And one of the ways to think about it is using the multivariate normal sampling scheme, with the mean being the ensemble mean, and the covariance that one can find by fitting the geospatial parameters of the range, sill, and nugget. But these climate model outputs, different climate model outputs in the same ensemble have dependencies such that they share the code, they share the data, and many of the components. So for example, this image shows the output from Norwegian Climate Center, which is in the CMIP5 ensemble, and another ensemble member from the same group, which uses a component of biogeochemical cycling, shows a similar output in the same ensemble. So to address this issue, we propose to use weighted multimodal ensemble mean. And the way we inform the weights are by clustering similar climate models. So the key ingredient in clustering is the similarity measure. So if we can find the similarity between these climate model output, then we can find a good weighting system and find a less bias in the ensemble estimate. So the way we propose is, the way we do is using the Riemannian metric between the covariance matrices. And the first step to that is to fit the covariance, the parameters of the covariance matrix. And now that these covariances lie on the space of symmetric positive definite matrices, we can use these canonical distances, one of them being the Riemannian metric on the manifold, and then cluster it to inform the weights. So here I showed two images. One is from the Euclidean distance between the climate model output, and another is from the manifold distance of the covariance matrices. And what's interesting is that the Euclidean distance have very little contrast, while the geodesic distance on this manifold has more contrast, which says that it has identified more dependencies and hence less bias in the estimator. Additionally, because we have this manifold of covariance matrices, we can leverage many of the recent advances in the field of information geometry to sample new covariance matrix from the distribution of covariance matrices. So to diagnose this sample, we use a standard technique in the geospatial literature, which is the semi-variogram plots, which gives a good intuition of how these parameters visually look. So for example, over here, from the standard multivariate scheme, the plots in the red shows the semi-variogram plots from the models, and that of the samples are the blue lines. And you see that the blue samples, the blue lines, the distribution doesn't emulate well all the models, specifically the NOVA model from the geophysics lab. But when we use our sampling scheme, we get the entire spread over all the models. And to investigate this further, show a spatial field of this NOVA model, and the sample, one of the samples which is close in the semi-variogram plot space, and then from the standard multivariate normal sampling scheme. And if you see the boxes, it shows that the proposed sampling scheme has more similarity in the patterns of the spatial field than that of the standard multivariate normal sampling scheme. And finally, this manifold of covariance matrices of climate model outputs could be useful to investigate further the interdependencies in the SIMIP-Phi ensemble. And the proposed estimates could be potentially used to mimic the existing climate model outputs, so that we can get a rather quick realization of different scenarios of a future climate, rather than waiting for several months to see how the climate model output looks. Thank you.